Okay, after some technical problems, let's go into statistics. Today, well, we are still at the regression, and last time we generalized our simple linear regression so that we went on with now the so-called multilinear regression that we said we had many independent variables which influence some other variable, and this we model again in a linear way. So conceptually, everything is the same, but then this will mean that we come just from this simple linear equation, y is a plus bx, we have to go to the vector and the matrix description. But if we are used to it, we also write this again as y vector equals matrix A times beta vector plus a vector of arrows. And about these arrows, we will start to talk today. But at first, we then just did more or less everything like we did it in the simple regression, but only we have now the problem that we have to solve our target function, which is again the sum over all squares to be minimized with respect to all our parameters in front of our independent variables. There we have to manipulate the writing of these sum of squared errors, and then we have to do the multidimensional derivative. Well, actually, we did it already also in the linear regression part. There we had two parameters, a and b, and now we have n parameters, beta. So we have to calculate n different derivatives, but still the derivatives looked more or less, again, only with vectors and matrices, quite the same as in the simple linear case. But then we have a practical problem, because in the simple linear case with only two variables, we can't just solve our problem by dividing by a number. And here we have this optimality condition, and we are looking for this parameter beta, but in front of this parameter vector beta, we have a matrix. Well, and so to speak, we can divide by a matrix, but this will in practical mean that we have to calculate the inverse of this matrix, and this is not a simple problem in order to do this. Well, theoretically, we can just write here, multiplying from the left with the inverted matrix, but in practice, this is quite a problem, and to do this by hand, if you have 3, 4, 5, 100 parameters or something like this, this is very hard to do this. In our times today, we can do this with our computer, with some software package, but still, this is then an algorithm where we do approximations. This you have also to keep in mind. Theoretically, everything is solved, but for practical issues, we cannot do it without a computer, not in finite time. Okay, this we did then also with one example. I showed it also to you to do it, so to speak, by hand within Excel, and hopefully from this you have an idea what happens there if you calculate it. Because of course you have also your software packages where you just only feed in the data, pressing enter, and then everything is on the next screen. But I hope that you have from this somehow a little bit of understanding what you are doing there later on if you are just feed in the data and press enter. Yeah, but after we have calculated our parameters beta, we are still only in the descriptive case. And of course, for every data set, we can just calculate these parameters beta, and from a descriptive way of interpretation, we can say this is for x1, x2, and this is the parameter for xb. Beta 0 is just in the simple case the cutting point on the vertical axis. And this 0.4, then, what was it here? Visits would mean that we increase our visits by 1, that this would have an impact on our sales of roughly 0.4. Or if we increase our marketing budget by €1, this would mean from this descriptive analysis an increase of sales of 50 cents, maybe. Well, from a descriptive way, if we take then the interpretation here for marketing, well, investing €1 and getting out only 50 cents, we will don't do it, maybe. But this is only the descriptive part. So what we right now do not know is how reliable is my estimation here. Because in general, I don't have the full data set, or in my company, I have some historical data. And then I will say, well, how reliable is the outcome of these parameters that this really will happen in future? So what is, so to speak, the probability if I open a new store? Then my regression say, well, even if you open your new store, then your sales will fall. And then I ask, well, but I want to go into the market. What is the probability that this really happens, what I'm just calculated here from my data? And this is then the so-called hypothesis testing. Because until now, we have no causality. We have only calculated correlations. From our data, we have this dependence between these two variables. But we don't know the reasons behind this. About the full data set, I have already talked about. Well, and if you also keep in mind these picture of the two-dimensional part of the simple linear regression, then we also know that our data is fluctuating around our linear line. And that if we then assume, for example, if we want to make a forecast for the revenue of our company, extrapolating the linear line, that, of course, there is an error. And what we want to do now is to discuss assumptions, especially about the dispersion of these error terms, so that then we can statistically make an announcement that maybe I can rely on my outcome of my linear regression with 95% or something like this. Still, there is a risk that something other things happen, but then I can say with probability 95%. And maybe this is for my decision in my company enough. Okay. And what are the assumptions which we are make now so that we can really do then these hypothesis testing? Well, the first one is that in general we say we have the equal probabilities that we are too high or too low with our estimation. And this seems to be a very reasonable assumption in order to get a good decision procedure, because, well, we want to have that we somehow in the middle with our estimations. But we have to keep in mind this is an assumption that the expectation value of our errors is just 0. And the next one, and there we have, I think, 1 or 2 topics about, and this is a very, very strong assumption which we make. We have n variables, independent variables. And what we now assume is that every single error is associated with one variable x1, x2, x3, and so on, that all these single errors are independent from the other one. So that all errors are independent, and also we specified our model in a proper way so that the independent variables which we feed into our model are also independent. And maybe you already have an idea why we are doing this, because otherwise we would have to deal also with internal correlations within our model. And this will be very, very complicated then. But of course, in practice, it is really hard to find variables which did not influence each other. Of course, somehow the HR department depends on the marketing department and so on. But maybe, and this is then, I think we have one topic in the term papers. This was about misspecifying our model, that we have to deal with the problem that in practice we know that there are dependencies between these variables. And then we have to ask ourselves, well, can we somehow make some tests in order to find from the data which variables are influencing each other? And also we know that this assumption that the errors are independent, that we more or less will not not find in practice. And what does this mean? if these variables are dependent and the errors. And then a very, very strong assumption is also to make the calculation as easy as possible. We assume these variables are independent, but they all have the same variance. And this is also a topic which we have in the term papers. This is the so-called homoscedasticity assumption. And the topic, I think, is then called heteroscedasticity. And of course, in practice, in most cases, we will have the case that these variances are differing for different variables. Well, and these two, of course, are highly dependent, but yeah, in general, we also assume that the covariance for all variances or for all pairs of errors is also 0. And this is also a topic in the term papers. This is the problem of autocorrelation. And this is then, yeah, as I already told here, the question, what is the direction of causality? Well, and you know, I'm a macroeconomist, and think of total income. There we are writing income is consumption plus investment plus government expenditure, and especially we say consumption is dependent on income positively. Well, and now what is now the direction of the causality? Is consumption influencing income or income influencing consumption? In practice, we know these are both sides, but if you want to do rigorous statistics, there you have to distinguish. Because otherwise you have the problem, where do I start? Where I can anchor my problem? Well, and this is philosophically spoken the problem which was first, the hen or the egg. And the last one is we assume that all our errors are normally distributed. Well, in general, we know also that this is not the case, but of course, this we can motivate by the central limit theorem. And this means, well, if I need, so to speak, if I have, so to speak, enough data, then I know, although I know that I do not know which is the distribution of my errors, I can say if I have a huge amount of data that approximately I will go into the direction of the normal distribution. By the central limit theorem. But of course, we are in economic science, and what we are dealing with in economic science is we are dealing with ourselves, because we are the economic agents. And yeah, especially people have a problem with statistics because we always are free to decide in the other direction. And for this, especially if we go to economic data or if you go to finance data, then we really see that we find also, if we have very much data, that sometimes the assumption that something is normally distributed is not a good assumption. Because especially if we go to social science, then we see, and you know this Gaussian curve for the density function of the normal distribution, that especially the probability for events in the extreme part of our distribution due to the density of the normal distribution is very, very low. Remember, this is roughly f of x e to minus x squared. And you know the exponential function, this goes very, very fast here in the neighborhood of 0. And here you even have also the square. When you have minus, this means that is 1 over e to x squared. So you have the exponential function and you have the squared here. And this really dampens your function if you are at in absolute values on the left for large x or at the right at large x. But then we see in financial and economic data, so like the huge crisis, economic crisis we had during the last 15 years, this should not happen that often as we have seen it. Due to the normal distribution, this would be very, very improbable that within 15 years we have 3 drastic economic crises. And also, if you go to the ups and downs at the stock market, they are also the extreme event happens much more often than we would think of it if we assume that stock market prices will follow a normal distribution. So it could be very good motivated, but then of course we have also to ask, can we with this assumption describe the real world? And then we have sometimes to admit, well, we have to look at another modeling. But for us now, we will assume or we make these 5 assumptions, and I already mentioned it in some of your term papers. You have to deal with these assumptions, and if we are not assuming this anymore, then of course we still want to do statistics, and what can I do then? Okay, so but now yeah, we want to talk conceptually what we now want to estimate, and if we calculate then an estimator where we later on want to say, well, with a probability of 90%, I think that this is a good estimation. We have also to talk about properties which these estimators should have, so that we say this is in principle a good estimator. So these assumptions or these properties which I show you now, this is not some natural law or something like this. That it has to be, or that estimators have to have these properties, but these properties are discussed properties, and this developed during the last 100, 150 years, where mathematicians, statisticians thought about, well, what would be for practical issues good properties for our estimators. Well, and one we already talked about when I showed you the variance, that the variance we calculate from the data is not 1 over n, but 1 over n minus 1, x minus x bar squared. And that this factor in front of the sum, which is not intuitively clear, because in general we would say if we want to calculate some number for the dispersion, then we would say let's do it like the arithmetic mean, taking every single dispersion and divide it then by the number of my data set. That would be intuitively clear. But then we have shown that this estimator, if we calculate the expected value of this estimator, would not meet the true estimator if we would know the true estimator. And from this calculation then came out that we have to divide this sum not by 1 over n, but 1 over n minus 1. Well, and why do we call this, or we call this then an unbiased estimator? Because the expected value will meet the true value. Well, and I think this is then pretty clear that this is a quite good property of an estimator, because what do I want to have if I calculated this estimator from data? Then it is quite clear that I want to have then an estimator where I can say, well, I know that I'm making errors, but to have a too large or a too low estimator, that these probabilities are more or less the same. And by mean, I'm really at the true estimator. So, therefore, this is one property which I want to have. Well, then, of course, I can say that I know almost with probability 1, I'm not coming out with my estimator at the true point only in the expected value. I know that I'm above or below the true value. But then it would be also a good property that the distance or the error of my calculated number will be as small as possible. And for this, then I make the so-called assumption, or I want to have the property that my estimator is efficient. And what is the understanding of efficiency? The understanding of efficiency is that the dispersion of my unbiased estimator is as small as possible. So from this property, I can calculate many estimators. Let's say 50 different types. And all these estimators have these properties. And then I look at every calculated estimators, and then I calculate the variance of all these estimators. And then I just pick out this estimator which has the lowest variance. And then I call this estimator efficient. So unbiasedness and efficiency. What else can I do? Well, sometimes I have to admit that I cannot really find an unbiased estimator. And for this, they then look at estimators when I'm increasing my data set, the number of my data set. That I use then an estimator which will be as nearer in the neighborhood of the true estimator as larger the number of my data set is. So that I'm approximately in the neighborhood of an unbiased estimator. And this then I call the unbiased, the asymptotically unbiased estimator. Well, then is another property where I do not want to go in too much detail, and this is called consistency. Well, you from school or from your mathematics courses, you have maybe something seen that and n tends to infinity, that this meets then some special number. And this is then related to this classical asymptotically unbiased estimator. But if we are doing statistics, then we quite often have to use other limit concepts because we have these uncertainty because of our errors. And for this, then we introduce the, so to speak, the so-called stochastic convergence concepts. Well, maybe you can see or you can realize the problem we sometimes have if we take these density function. Then, of course, with the density function, we cannot speak anymore about an event having some special property. If we take a continuous distribution, then we have an uncountable number of events, and therefore we cannot anymore talk about one event has one special probability. And therefore, then we have to admit that every single event has a probability 0. And this goes also, in somehow a philosophical part that we can in statistics then say, well, there are events, but the probability of these events is 0. And from this, maybe you can imagine that we then have to use other convergence concepts. And this is then meant that we also need, or that we also want that our estimators, which we are calculating, not only meet our true estimator in the sense of a classical limit concept, but also in this statistical limit concept. Because otherwise it could be the case that we are more or less definitely wrong with our estimator. And this is called consistency, if you find this term in your statistics books, maybe. And the last one is the so-called sufficiency. And this, is again something about practical issues, because when we are calculating estimators, and especially if we have very large data sets, then we have to do many calculations. And this, of course, takes time. And for this, we then call an estimator sufficient if we do not use all information we have in our data set, but only the relevant information in order to meet afterwards the true parameter directly in the expected value or asymptotically. Because we are not interested in the end if when we are doing statistics on every information which we have in the data set, but we want only to have a good estimator for our true parameter. And in this case, sometimes we can skip many information which we have in our data and we do not have to use. And then, of course, we are economists. We have lower transaction costs in order to calculate these estimators. So all this, maybe if you just one time have a look in general or a theoretical decision theory. This was, a topic which I think more or less then started in the 20s of the last century. And then decision theory really started as a part of science. Okay. Then, now let's go back to our multiple linear regression, to our ansatz where we say y equals beta 0 plus beta 1 x1 plus beta n xn plus an error. So now we want to ask, what would be now good estimators for our parameters, and what would be good estimators for our dispersion around for the dispersion of our data around our theoretical model. Well, and for this, again, we could say, since we already know that dividing in the two-dimensional case, the sum of the squared errors not by n, but by n minus 1, then we could say, since we assumed, this was, I think, assumption 5 here. Yep. No, assumption 3. Since we assume that every single variance of our errors should be the same, that we could think, well, let's take this from the two-dimensional case to the multi-dimensional case, and again, let's just divide it by n minus 1. But again, and this I will not do with you, I think in some textbooks I gave you, there is shown the step from here to here, that this estimator will not be anymore in the multidimensional case an unbiased estimator, but what we can show is, here I have to take then k for the number, that we can say that if we take the number of our independent variables in our model that we have to recalculate this and that we do not have to correct our squared sum of the errors by 1, but by k plus 1. Well, and this is maybe heuristically seen here from our modeling, since just k plus 1 is the number of all of our regression parameters. And what this then more or less mean, this is a correction with the numbers of degrees of freedom in our model. Why degrees of freedom? Well, we are free to choose these k plus 1 parameters. And therefore, then we will take for the variance this parameter here. Well, if we take now these unbiased estimator and then we have to go back to our setup here. Where do I have it? Yeah, here we have the definition then of our errors. And with this, opala, this is too fast. We can then say that the error of all our estimators beta, which we have calculated in this descriptive manner I have shown you, that these are now given by the number we have calculated. So this is the variance of all error parameters epsilon I divided, not divided, but multiplied again by the inverse of our input matrix. Also remember this is just our input matrix calculated from our data set. So this is, if we have our data set, just a matrix where, after we have run all these things through our software package, or you have done it in Excel by your own, as I did it last week with you together. But this is a known matrix where we know every part of this. So here x1 to x1k and so on. All this is known. These numbers are calculated from our from our data set. And now where do I can this? I have to take again. Oops. Here we have it. This I need. Sorry. So then I can show it to you. So what we have is in the matrix description. This is x beta plus epsilon, and yeah, then we could write epsilon is y minus x beta and from this then we can say that we in the end only need from this matrix only the diagonal elements. So this would be then x11, x22 down here. And if we want then the explicit errors for every single parameter, so the standard error, then we just take, so to speak, the square root of this formula, but now only taking the diagonal elements. This means from this matrix, we are taking out this vector here. And this is then these are the errors for every estimated beta. Well, and now comes, yeah, a quite nice thing which we can now show from all these assumptions here. Because if we make these assumptions on the error terms in general in our model, then, and this is what we are interested for practical issues later on, of course, then we want to know how are our betas distributed, because then we want later on make make a statement of with 95% probability I'm in the neighborhood of the true parameter or something like this. But for this, of course, I have to know how are my betas are distributed. And from these 5 assumptions, then I can show that also my estimators are also normally distributed. And now with a normal distribution, just around the true parameter and with variances related to the general assumption that every single error term has the same variance multiplied with the corresponding diagonal element of these inverted matrix here. And therefore we see that in order to get these inverted matrix xt times x is more or less the central point of our regression. So more or less then the assumption about no correlation, same variance of all errors, independency and normal distribution of the fundamental errors feeds in through our model just to the end what I'm interested in and to the distribution of our betas. But of course, this is again not a natural law. This comes from our assumptions. And we have to admit that very, very often, if people are doing statistics in social sciences, they do not think about anymore about their assumptions. And especially that you can do only statistics when you can argue that in my case, what I'm now looking at, I could in a good manner motivate that these 5 assumptions which we have in general will meet in my special experiment. Only in this case I'm allowed to do all the statistics and making all the statements later on about probabilities and so on. Well, and in September I was at a conference. There was a very long talk about what was it? Yeah, there was just some questionnaire, and then in the end of the talk, then he said, well, we ask, I don't know anymore, 200, 300 people. And then the speaker made the statement, well, and now I'm doing statistics, and here I've shown with significance of 5%. What significance is, we will talk later on. I can say that the people acting like this with 95% probability or something like this. Well, the design of their experiment was just in a way that especially by the design of the experiment, they have not met this assumption here. Because especially they took the people they asked not in a random manner. So they had no randomly chosen data set. And then, of course, although I have asked 500 people, the assumption that everything is normally distributed is definitely not true anymore. And also not true in an approximate way. Well, and just in the end, it was not me, but another one, he just, very politely asked, well, everything what you have done in the descriptive way, when you described your experiment and the outcome and everything is okay what you are doing. But please do not talk about probabilities and statistics in the end, because you are definitely not allowed to do it. well, within the room, then there was some rumors, but not very much. And then in the end, everybody has we're going to drink coffee and something like this. But this we really find very often that we do not think about anymore about these very strict assumptions, which we make in the beginning, and then afterwards we are doing statistics. And please keep this in mind, and this is what I mean, not just feeding in the data in the software package, pressing enter, and then talking about significance and probability and so on. Please keep this in mind in the future. Okay. So then, yeah, let's start with hypothesis tests in general, just for some minutes. And here I've written it down. Assume you have a random sample so that we really meet our assumptions. And now we want to test a hypothesis. Well, so I ask, I want to be on the right side with 95% probability. And then I'm looking for my data. So also what I have to then, and in my view, I always have to do it, then I have to think about what would be in my special experiment be a good limit for the probability. Is it for me enough that I'm right with 90%, or am I in some circumstances where I need 99% or whatever? But I think that every time you have to think about in your special situations, what is in my specific case a good or the right probability which I choose. And also this I find, or this I have seen also quite often, quite often I'm the second guy in bachelor thesis. And then you are sitting in the colloquium, and also the people did really good things about also having a questionnaire, but they did it in the right way. It was randomly chosen, everything is okay. And then quite often they talk about, yeah, well, and the outcome is that my result is significant. And then sometimes I ask, well, what do I understand by significance? And then also quite often it's said, well, significance is always 95%. And there, my opinion is this is not true. Well, we use very often 95%. But I think you really have every time to think about, is it okay if my limit is 5% or not? But there you will find also other economists and other scientists which just say, well, significance is always like a natural law, 5%. And I definitely say from my point of view, no. So to speak, what we want to do is we thinking about this probability of error, and we then want to make only an error with an error with this probability, the wrong decision. And this probability is then the probability, although our experiment shows everything is okay, since we are in a statistical experiment, still it can be wrong. Yeah, let's end today with this example. Again, taking an economic example, we have some marketing activity. And why we are doing marketing? Well, we want to sell more in the future, and quite often we are doing marketing because we want that more people know our product. So what we now want to test from a questionnaire, from some data, since when we have increased in history our marketing, has this really increased the awareness of the product? And so before I have started my marketing activity, we assume that we have asked 1,000 people, do you know our product? And maybe we have seen from this pre-experiment data set, roughly 40% of the people know our product. Now we have made our marketing activity, and again, we ask randomly chosen 1,000 people, do you know our product? And within this new sample, now 420 people answer, well, I know your product. And now the question is, of course, 420 is larger than 400. So now 42% of the people say, yes, I know the product. Can I then say, well, my marketing activity was a success? Because the awareness of my product has descriptively risen. But of course, we have chosen here randomly 1,000 people. And maybe only by chance, I just got many people who are knowing my product. If I take another 1,000 people, maybe then I count only 385 people. And again, I have the problem, it is too costly to ask everybody. And for this, then, in order, how good is, for example, in this case here, my hypothesis from this data set, with which probability I can say, yes, more people know my product. And for this, then I make the so-called null hypothesis. And why I call this the null hypothesis, or we call this the null hypothesis? Well, this is, so to speak, our anchor. And our anchor is, we have done something. And our anchor is, well, you have done something, but nothing has changed. And this is very, very often, the thing we are interested in. We want to know, since we have done something, has the world changed or not? And what we will do then tomorrow is to formulate then these hypotheses. And here, then, for example, I assume that although I find here 400 people has answered yes, nothing has changed. And this hypothesis that nothing has changed is wrong only with 5%. And then I will test from my data And from my assumptions about the distributions, normal distribution and so on, can I reject this hypothesis that nothing has changed? And very, very often I formulate it like this, that I want to have the case that I can then reject these null hypotheses. And in opposite, then I can say, well, of course, with probability 95%, then I can say the world has really changed. And how we can do this, we will talk then tomorrow. Thank you very much.